In this video, I'm going to define what we mean when we say a numerical scheme is consistent with a differential equation. Building on material presented in previous videos on finite difference schemes for the advection equation, I'll examine numerical diffusion and the consistency of the first-order upwind explicit scheme for advection. Consistency of a numerical scheme is a measure of the extent to which the exact solution satisfies the discretized problem. Thus, for example, if we have two independent variables x and t, and a numerical scheme with grid spacing delta x and time step delta t, then the scheme is consistent with the original PDE if, when delta x and delta t tend to 0, the scheme tends to the original PDE. In order to say something about consistency of a scheme, we need to perform truncation error analysis. To illustrate, I'm going to use the example of the first-order explicit upwind scheme for the advection equation. Throughout this video, the examples I will use have independent variables x and t and a dependent variable c. We thus have a computational domain in the xt plane as illustrated here. For the numerical schemes, we're going to impose a regular rectangular grid onto this domain with cell spacing delta x and time step delta t, and we're going to use the notation Cij to denote c evaluated at position I delta x and time j delta t. Here's the finite difference equation for the first-order upwind explicit scheme for the advection equation. If we look at the individual terms, on the left-hand side we have Cij plus 1. Let's look at the Taylor series expansion for this term. We have Cij plus delta t dc dt plus delta t over 2 factorial d2c by dt squared plus delta t squared over 3 factorial d3c by dt cubed plus higher order terms. Similarly, looking at the term Ci minus 1j on the right hand side, we have this Taylor series. Substituting these two series into the finite difference equation, we have this equation. Some of these terms will cancel. We have a Cij term on both sides of the equation, and we have a minus rho Cij and a rho Cij term on the right hand side. Thus we can rewrite our equation as shown here. Next we note that since the Courant number rho is defined as u delta t over delta x, we have rho delta x equals u delta t. If we look at the coefficients multiplying the derivatives on the right hand side of this equation, we can see that rho delta x can be replaced by u delta t, yielding this equation. We can now divide both sides of the equation by delta t, giving us this equation. A simple rearrangement yields this equation. Now, if we remind ourselves of the problem we're trying to model, the advection equation states that dc by dt plus u dc by dx equals 0. Thus, the right-hand side of the equation we have generated is the truncation error of the numerical scheme. It's a measure of the difference between the advection equation and the finite difference scheme. If we want to know the order of the error, we need to look at the leading terms in the truncation error. We can see that the first two are first-order accurate, and the second two are second-order accurate. We call those first two terms the local truncation error of the scheme, and they confirm that we have a first-order scheme. More importantly, though, they tell us the exact form of the error. Now that we have an expression for the truncation error, we can establish whether or not this scheme is consistent. Remember, the scheme is consistent with the PDE, which in this case is the advection equation, if the scheme tends to the original PDE when delta x and delta t tend to 0. Here we can clearly see that the limit of the truncation error, as delta x and delta t tend to 0, is 0. This implies that the scheme is consistent with the original PDE. This method for proving consistency is called truncation error analysis. Let's now examine the local truncation error more closely. We know from the advection equation that dc by dt equals minus u dc by dx. Differentiating with respect to time, we have d2c by dt squared equals d by dt of minus u dc dx. Now, minus u is a constant, so that can come outside of the differentiation. We also know, and this is a standard result that you can look up, that the order of partial differentiation can be swapped, giving us minus u d by dx of dc by dt. Again, we can replace dc by dt by minus u dc by dx. Finally, again bringing minus u outside the differentiation, we can see that d2c by dt squared equals u squared d2c by dx squared. Substituting for d2c by dt squared in our equation for the local truncation error, we get this expression. Noting as before that rho delta x equals u delta t, we can rewrite this further, yielding the equation LTE equals a half u delta x 1 minus rho d2c by dx squared. This term is the source of the numerical diffusion we observe in solutions using this scheme. Let's examine this in more detail. First, we note that the local truncation error is proportional to d2c by dx squared. Looking at the equation we derived from the numerical scheme, we can see clearly that this is of the form of a diffusion term. If the Courant number ρ is less than 1, this term is positive and it has a diffusive effect. This is called numerical diffusion because it arises from the numerical scheme we've chosen. If ρ is greater than 1, it's negative and has an amplifying effect. This is a cause of instability. When ρ equals 1, the local truncation error is 0, and there's no numerical diffusion. We would expect this to increase the accuracy of our solution, since the leading term in the truncation error has been eliminated. We can also see that when ρ is close to 1, this term is small, and thus so is the numerical diffusion. Elimination of this term using additional Taylor series expansions leads to higher order methods, which tend to be more accurate and less prone to instability. Let's now review some results obtained using this scheme in the light of this analysis. First, consider the case ρ less than 1. In this example, ρ is 0.5. The blue curve on the graph is the initial distribution, the orange curve is the exact solution, and the green curve is the numerical solution obtained using the parameters shown. As we've seen, the local truncation error in this case is positive, and we can see from the graph that it has a diffusive effect. Second, we see the case ρ equals 1. Here the local truncation error is 0 and there's no numerical diffusion. In fact, in this special case, the higher order terms also become 0 and the exact solution is reproduced. We looked at that in the first video investigating this scheme, where we saw that information is propagated along the characteristic in this case. Third, we have a Courant number greater than 1, in this case 1.2. Here the local truncation error is negative and has an amplifying effect, leading to instability. Finally, we see an example with a slightly higher Courant number, showing more clearly the oscillations and amplification that lead to instability. In summary then, consistency of a numerical scheme is its property that when the discretization steps tend to 0, its finite difference approximation tends towards the original differential equation. In other words, its truncation error disappears when the discretization steps tend to 0. Thus, if we want to prove that a scheme is consistent with the differential equation it represents, we have to perform a truncation error analysis, which we did for the first order upwind explicit scheme for the advection equation. We also looked at numerical diffusion, which is a property of the numerical scheme, and saw how it can arise from the truncation error. We saw that numerical diffusion causes inaccuracy in the solution, providing some motivation for deriving schemes based on higher order approximations to the derivatives. Finally, we saw that the truncation error can cause amplification of the numerical solution, leading to numerical instability. This will be explored in more depth in the video on stability. It's worth noting that we proved that the first order upwind explicit scheme for the advection equation is consistent with the advection equation, and that this is true regardless of whether the scheme is stable or unstable.